Have you ever wondered how a service can handle millions of requests a second without even breaking a sweat? Well, today we're going to pop the hood on one of the true workhorses of the internet, Amazon DynamoDB. We're going way past the basic API calls to really understand the deep engineering that makes a database at this kind of hyperscale even possible. I think a great way to think about this is like having a high-performance sports car. Sure, you could drive it around town stuck in first gear, but you'd be redlining the engine, burning through gas, and wondering why it's so clunky and loud. To really feel its power, you've got to understand the machine. You need to know when to shift gears. And that's exactly what we're going to do today. We're going to learn how to drive DynamoDB the right way by understanding what's really happening under the hood. So here's our game plan. We'll start small with the life of a single request. Then we'll zoom out to see how data gets organized across the entire system. We're going to tackle that tricky problem of scaling, look at some safety features, and then finish up with the real secret sauce that makes it all work. Look, the whole point of this explainer is to go from being just a user to being an informed user, because knowing this stuff isn't just academic. It's going to directly help you design applications that are faster, more efficient, and cheaper to run on DynamoDB. All right, let's start with the absolute most basic building block, a single API call. What actually happens when you ask DynamoDB to get or to put just one little piece of data? A GET request, just reading data, is actually pretty simple. Your call first hits something called a request router. The key here is that it's stateless, which means any router in the whole fleet can handle your request. It's like checking your ID. It authenticates and authorizes you. Then it uses a map to figure out exactly which physical server is holding your data, grabs it, and sends it right back. Super simple, super fast. Now, a put request, writing data, that's where things get more interesting, because here, durability is everything. Your data can't just live on one machine, right? What if it fails? So the request goes to a very specific storage node that's been designated as the leader. The leader writes the data to its own disk and then immediately sends copies to two other nodes in different data centers. But here's the clever part for performance. DynamoDB doesn't wait for both copies to be saved. As soon as just one of those replicas says, "Got it," DynamoDB sends a success message back to you. It trusts that the third copy will catch up, which is a key trick to keep things moving fast. So you might be wondering, how do these three different server nodes decide who gets to be the leader? How do they avoid arguing? Well, they use a classic, famous algorithm from distributed systems called Paxos. You can just think of it like a super formal, lightning-fast election process for computers. They use it to all agree on one critical thing. Which one of them is the single source of truth for all writes? This is absolutely crucial because it prevents a situation where two different nodes could accept conflicting updates for the same piece of data. Paxos ensures consistency. Okay, so we've seen how one item gets handled, but what about a table that has billions or even trillions of items? DynamoDB doesn't just stuff all that into one giant file cabinet. The magic here is something called partitioning. DynamoDB takes the primary key of your data, runs it through a special math function, a hash function, and the result tells it exactly which logical bucket or partition your data belongs in. Each of these partitions is its own little self-contained world, with its own leader and its own two replicas. It's the ultimate divide-and-conquer strategy for handling massive data sets. Now, this partitioning leads us right to that famous term, eventual consistency. And it's not as scary as it sounds. When you do a standard read, the request router can ask any of the three nodes for your data, the leader or either of its two replicas. And since we know the leader and at least one replica are always perfectly in sync, that means you have a 2 out of 3 chance of getting a perfectly up to the millisecond consistent read. At worst, there's a 1 in 3 chance you hit that third replica that's still catching up, which is usually just a few milliseconds behind. Okay. This is where things get a little bit wild. A simple update doesn't always stay simple, especially if your table has what we call secondary indexes. So just imagine, you're making a single update call, just changing one little thing on one item in your main table. Seems pretty small and insignificant, right? Well, that one little update can actually trigger a cascade of operations that touch up to 11 different partitions. Yeah, you heard that right, 11. It's a concept called write amplification. Here's how it breaks down. You have the one write to your main table, but if that update also changes the value in, say, 5 of your global secondary indexes, the system might have to delete the old index entry and write a new one for each of those 5 indexes. So that's your 1 base table write plus 10 index operations, potentially involving 11 completely separate partitions. Wild. And all this complexity leads us directly to one of the trickiest parts of using DynamoDB historically, managing capacity. How do you give your table just enough horsepower to handle its workload without totally wasting your money? This is the classic balancing act, and if you've used DynamoDB, you've felt this pain. Set your provision capacity too low, and your application starts getting throttled, users see errors, and everyone's unhappy. But if you set it way too high just to be safe, you are literally just paying for server capacity that's sitting there doing nothing. It was a really hard problem to solve manually. So over the years, AWS layered on more and more sophisticated solutions. First, there was bursting, which let you save up a few minutes of unused capacity in a token bucket to handle short little traffic spikes. Then came adaptive capacity, which was really smart. It could borrow capacity from all the idle partitions in your table and give it to a single hot partition that was getting slammed. And finally, we got auto-scaling, which is the real game changer. It just watches your table's actual usage and dials the provision capacity up or down for you automatically. Okay, so our data is durable, our table can scale, but what about recovering from a disaster? Or what about serving a global audience all around the world? Well, the secret to all of these amazing features is that replication log we talked about, that same stream of changes from the put request. It is a foundational building block for so much more. That log is continuously streamed over to S3, which is what enables point-in-time recovery. It's also what's exposed as DynamoDB streams, which lets you build these cool event-driven applications that react to changes in your data. And it is the literal engine that powers global tables by replaying that same log in other regions around the world. It's just a brilliant piece of engineering, using one core mechanism to power multiple powerful features. All right, let's wrap this up by looking at the invisible system that pulls all the strings, the thing that makes DynamoDB actually work at a scale no human could ever hope to manage. They call it the auto-admin, and you should really think of it as a tireless, fleet-wide, robotic database administrator. When a partition gets too big or too busy, the auto-admin splits it in two. When a physical server fails, the auto-admin detects it, moves its work elsewhere, and replaces it, all without a human ever getting paged. It is the absolute heart of the service, automating away all the insane operational complexity of running a database at this scale. So after this whole deep dive, what are the big takeaways? First, your data is kept incredibly safe through a clever three-way replication system that's governed by a Paxos elected leader. Second, those massive tables are made manageable by splitting them into partitions, and knowing that is key to avoiding performance hotspots. And finally, this entire incredibly complex system is run by the invisible hand of the auto-admin, and that is what truly makes DynamoDB a managed service. And that leaves us with one final big thought. We've just seen the mind-boggling complexity hidden inside DynamoDB, and the amazing automated system that's required to tame it. As our whole digital world gets more and more complex, is this the future for all technology? Will every major service we rely on eventually need its own intelligent auto-admin, just so we humans can still use it effectively? It's something to think about. Thanks for tuning in.